Very pleased to welcome our second speaker, Paul Seidel from IT, who will tell us about second-order ODEs and the mirror map.
Thank you very much for inviting me. For those of you who are wondering, is this essentially the same talk as this general in Miami, which was also essentially the same talk as the previous general in Miami? The answer is more or less yes. So I decided instead of actually solving this problem, I would just sort of circle round and round it until some of the younger people get so bored that they just solve it. Okay? So part of this has to do with my inability to understand mirror maps, which is sort of something that everybody else got over in the mid-1990s. Okay, so this is a standard mirror symmetry talk. In this side, the B side comes first, and then comes the A side. Okay. So let X be a smooth algebraic quantity, which is Calabi-Yau, so it comes with a algebraic volume form. Okay. And I want to look at its Hochschild cohomology. And for the purpose of simplicity, I will just identify it with what the Hochschild-Kosten-Rosenberg theorem says that it is, the cohomology of the exterior powers of the pendulum. Okay? So this carries a product of this exterior product and the Lie bracket, which will not play a major role in this talk. And so in particular, the product has a unit which is this guy here. So far I haven't actually used the fact that we're on a Calabi-Yau. Because we're on a Calabi-Yau, it also carries the BV operator, which is essentially the following thing. So if you take the ith exterior power of the tangent bubble, then because it's a Calabi-Yau, that can be identified using eta with n minus I forms. Then you have the exterior operator, exterior differential, and then you go back. And so this induces an operator of degree -1 on the Hochschild cohomology. So we also have cyclic cohomology, which I will call S1 a covariant Hochschild cohomology. And it's defined as follows, so take U, a formal variable of J, and then I will use this notation here as if I knew derived algebraic geometry. So it is, so I start with rho x, and now I add this u, and then comes tx and u times delta, and so on. Okay, dx u. And it is the hypercohomology of this complex. So obviously, what happens here is that if I take this gentleman and I set u equal to 0, then you land back in ordinary. And And the kernel of this thing here is given by the image of the multiplication by U map. And so we have this kind of, this is a long exact sequence. Okay? So if you take this guy here, and you tensor it, let's suppose we're going to complex numbers. So, I mean, you know, so here I introduced this variable u in part so that I could make this sequence here, and in part so that the differential had degree 1. Now what this means, you know, if you think of these things here as being identified with differential forms, here what we're trying to do is closed forms divided by u times exact forms, which is not exactly what you want, right? But if you assume u is invertible, then that gives you the Durand homology, which is just the same thing as topology. Okay, so so far I've worked now. So now assume that X is in fact a family of Claviels, depending on a parameter Q. Now, you can give this a variety of formal meanings that any of those meanings will do. So just choose whichever you're more comfortable with. Oh, actually, let me call this T. Okay? So then, so there's a class here, K, so the Kodaira-Spencer class, which lies in HH2, well, it lies in H1 of X, Tx, inside HH2 of X. Okay, so measuring the variation in dt direction. Okay, so that basically measures how your variety changes in dt direction. It does not involve the holomorphic volume form at this point. Okay. So the
can I ask a question?
yes.
Is anything you're going to say going to depend on the fact you have actual Calabi-Yau variety as opposed to Calabi-Yau category?
Well, no. However, while everything I've said so far translates into the world of Calabi-Yau categories, you know, without any issues, at some point you will start seeing things that's not obvious to you how to interpret them in non-commutative geometry, and that's actually in fact part of the point of trying to. Okay? But obviously, I will not use anything that, I'm trying not to use anything that's specifically geometric, right? So for instance, you know, I'm using exterior powers of the tangent bubble instead of differential forms, because they have a ring structure. Of course, differential forms also have a ring structure, but that does not translate well into a more general context. So very good. So the standard way to analyze, you know, how these how the complex structure and the algebraic volume form together depend on this parameter is to use Gauss-Manin connections. So what is a Gauss-Manin connection? Okay. So the Gauss-Manin connection is maybe I should say like this. So it goes from and it satisfies the following thing. If you take a function of t and you multiply x with I would like to say that that this is a connection in dt direction, right? But you cannot define a connection in dt direction in this guy here, because remember there's closed divided by u times exact, so it contains all the closed forms. And closed forms cannot be, parallel transported from one value of t to another. So instead what's true is that, this is like u times a connection, right? So if it was a connection, you would have this guy here, and it would have degree 0, and multiplied by u, and it satisfies this degree. Okay? And so this guy here exists, and so so here you see that it satisfies this form here, right? So if you set u equals 0, then this guy here disappears. Which means if you take gamma and then you specialize to u equals 0, you get something which is not a connection, it's an algebraic operation. It commutes with functions of t. And which algebraic operation is this? Well, it's just the product with the Spencer class. Plus 2. Okay, this is a form of, I don't know what, Griffith's transversality or something. So okay, so remark. So both this identity class and so this S1 equivariant, I mean the S1 equivariant cohomology does not have a ring structure, so it doesn't make sense to say what is the unit, but this element E that I defined out there, it lifts, because for obvious reasons, you just look at the chain complex, it sits in a part where it's kind of affected by U, and the same thing, and the Kodaira-Spencer class also lifts to an equivariant class. There's two ways of seeing this. Either you can say, well, there's a refinement of the Kodaira-Spencer class which governs the deformations of the variety together with its volume form, and that would already sit in here. Or you could just say, well, look at this diagram here. You start with the lift of E, and you apply gamma, you get a lift of K.
So it says use gamma E for K? Sorry, what?
Gamma of E. Right?
Yeah.
So once you have an equivariant lift, a lift of E, you apply gamma, and you get something which reduces to K. Thanks. So usually, what you do at this point here, right, in the way that I formulated it, is you say, well, first of all, let me invert U to get rid of the extra jump. Yes?
So the first way you described making K involve the homomorphic volume form.
Yes?
The second way did not seem to, but did gamma secretly involve this?
Well, no, I mean, of course, if you write gamma as, if you want to write gamma in a way that does not involve the homomorphic volume form, you have to write it on something that operates on differential force. Right? So, okay. So the usual way to proceed here is to say, okay, so first of all, I'm going to invert U, so get rid of the extra jump, and I end up with something which is a finite rank module over this thing here. And then I do the following thing. I start with E, with my preferred class, and I apply gamma. I get a new class, and then I apply gamma again. And eventually, because it's finite dimensional, I will run out of classes. And so, if you think gamma is some kind of derivative, so the kth derivative is going to be linearly dependent on the previous ones, and I write down a differential equation, which is called a Fuchs equation. Okay? So, so this is what you usually do. This is actually not what I want to do. So now I'm going to do something which, on the face of it, seems to be ridiculous. Because, why is it ridiculous? Because this measures the variation of x. If I say it's 0, It's nothing happening, right? The whole point about Gauss-Manin theory is to account for the fact that you have non-trivial variations of the complex structure. But, okay, we'll argue about it. Okay, so let's see. So one thing is the following one. Let's just be very formal to start with, right? So, as I said before, you should think of gamma as u times a connection, in principle, right? However, there's no connection which it's u of, right? If gamma was actually u times something, then when you did this, it would be 0, right? So the problem of not being u times something is exactly this k. Okay? So if I assume k equals 0, I can actually define a connection. So there are connections, which means actual operators in dt direction on this guy here. Use this one, so the equivalent connection. This one. And corresponding one here. So that indeed gamma is obtained by taking the first one and multiplying it by u. Okay? So you can divide by u and get this connection. In fact, there's even a connection which is, that expresses just how stupid the situation is. Because these guys here are just vector fields, and suddenly you can actually transport vector fields to infinitesimally closed fibers. Okay. So, okay. So, what I will try to do is so when I do, I'm going to assume this, and then I will try to think about something like a Picard-Fuchs equation, but for these guys here, okay? Because this guy here is almost the same thing as the Gauss-Manin connection, so in a sense it makes very little difference. And this guy here is closely related to that one. However, the advantage is that this thing here is a ring. Okay? So in here I can, partial cohomology is a commutative ring, so in here I can write down differential equations which are nonlinear. So let's make an example. So that, is that
an advantage?
Is that? Well, it depends on what the differential equations will say. Okay? So, okay. Okay, so consider the simplest, so this is actually not, so what is a case where this assumption can actually hold, right? A simple case. So consider x actually independent of t. Okay? But with a t-dependent beta. Okay? So then, well, so what happens then? Well, then you can, in principle, you can take anything. So x is independent of, so it means x is independent of t, means that, you start with some fixed variety over c, and then you multiply it with a t line and extend constants or something, right? So you can, so this means that you have ordinary differentiation in t direction.
Are we discussing compact or non-compact?
No, compact is not a good idea. Okay, so let's see. So how is this connection? So in this case here, so I have my connection here, and it actually comes from a local operation. And what is this local operation? Well, so, this is somehow supposed to relate it to the Gauss-Manin connection, and the Gauss-Manin connection is just given by differentiating forms in dt, right? And the only problem is because I insist of doing it for vector fields, so it looks like this. Okay, so this is what delta is. So nabla, sorry. So so in particular, so what happens if I take the function 1, which I, as a Hochschild cohomology class, I'm going to call this E. Okay, so it's the function 1. So it's the function 1, you map it to eta, right? Then you differentiate eta by dt, which is, it has a t dependence. And then this will be a volume form, and then you go back to thinking of it as a function. Okay?
There isn't any plus 1 in the second differential forms?
No. This is d by dt, right? So I have a family, I have this, x is essentially something fixed, cross a t line, and you differentiate d by dt in t direction. It's not fixed derivative. Is it? Just an ordinary derivative. You take anything, a function or something, differentiate it in t direction, right? There you go. Okay, so this thing here is actually dt eta over eta. Okay, I'm sorry I write it as partial derivative. There's only one direction, t, that we're interested in here. Okay, so this is dt over eta. So this is a function. Maybe you want to think of it like this, and let's call this little a. Okay, this guy here. So this is a function. More generally, and in fact, if you take anything, so a polyvector field, you could of course differentiate polyvector fields in t direction in this case here, but as this example shows, that is not, that's, if this was the formula, that should be 0, so in fact it's plus. Okay. So, so far there is still a sort of whiff of absolute triviality in this. So, so now let me, let me look at a specific example. Okay? So specifically, okay, so I start with something. This is what I'm actually interested in. A Calabi-Yau fibration. Now this can have various meanings. I mean, there can be singular fibers, but for me, what's important is that the canonical bundle is isomorphic to Okay, so the simplest thing would be a rational elliptic surface. So this means that obviously all the fibers are Calabi-Yaus, right? But also if you remove one of the fibers, it's also Calabi-Yau. The complement is an open Calabi-Yau. Okay, so in particular, there is a from eta 0 is a pole at x. Okay, so now what can I do in this context here? As I said, there are two choices. One is second victim today. Okay, one is to pass to just the fibers of this thing here. So there's a fiber at any point t. Okay, and the other is to remove that fiber. Okay, so So from the point of view of the Gauss-Riemann connection, this doesn't actually make a big difference which one you take, because there's a residue map from the cohomology of degree I of the complement to the cohomology of degree I minus 1 of the fiber, and it's compatible with everything. In fact, usually that's how you compute Gauss-Riemann connections on the fibers, by starting with the ones on the complement, and they're nice. But for me, it does make a difference, and I really want to take the complement.
Is it important for you here that it's there's one copy, that it's an O of 1?
Yes. Okay, you'll see for a second, because I want to say something quite explicit. Okay, so so now I'm going to take my family of t-dependent varieties, which is just going to be x bar minus the fiber at 1 over t. Okay, so I start with removing the fiber at infinity, and then I remove nearby fibers. Okay, so this is so this carries. So this depends on t, right, and algebraic in some sense. We'll discuss it in just a second. So this carries an algebraic volume form, eta, which is like that. So eta mod over minus. Okay? So if you multiply eta naught by this function here, you will acquire a new pole at the fiber over t inverse, and you will simultaneously remove the pole at infinity. Okay? So now we have this thing here, it's this family and the family of algebraic volume. Now, the point is that okay, so it's known that this Picard-Fuchs theory, this is a standard deformation theory with Kodaira-Spencer classes, does not always work as you would think it would for open varieties, right? Non-compact varieties. In fact, this one here, actually this class, the Kodaira-Spencer class, is actually always 0. Right? So what does it mean? Does it mean that this family is actually constant in T? Right? Well, now, before that I said, it's irrelevant for me how you think of a family depending on T. Now it matters. As a family of algebraic varieties over an actual complex parameter T, it is of course not the same for all T, right? But if you specialize it, say, to T equals 0 and consider it as a formal scheme, then it is trivial, actually. Because formally speaking, there's no difference between functions having a pole at a point and functions having a pole at infinitesimally close points. Okay? I will not elaborate on this. Okay, now let me see. So this assumption is always satisfied. In fact, we can use, even though it wasn't quite what I said, we can use the same formalism that I said here. So what is the, what do these things actually look like in this case here? So we have A is equal to dt eta over eta by definition, right? So I defined here. Fortified by my having taught calculus in the fall, I can compute this, and it turns out to be this guy here. Okay, so this is function here. So if I take the function and I try differentiating it here again, right? So I pick up, a square of this guy here, and then the pi goes up there, so it's pi r squared divided by 1 minus t squared, which is in fact a squared. Okay? So hence, okay. So what happens when I do my connection here? And I want to apply my connection, okay, to this identity I've done twice, right? So the first time, by what I said up here, right, you just get A. The second time, you're supposed to differentiate a, right, which gives you a squared, and add another a times a, which gives you a squared. Okay? So this differential equation, which you should think of as something like this, f prime of t is 2, f prime of t squared. That's the second order ODE. Right, well that doesn't seem, so I did what I said I would do, which is that I used under this assumption, I used this connection here, nabla, instead of the Gauss-Manin connection, and I applied it to the identity element twice, and I got a nonlinear second order ODE of a very simple kind in this space here. Okay, so I think we can agree that this is simpler than the typical Picard-Fuchs equations. So what is the point of this actually? So that, even taking into account the specific, so this is specific to this geometric framework of things that are phi beta over CP1, right? And as you see, I actually use the fact that the probably of order 1, otherwise you get something else. But even in this specific geometric framework, there are two choices that I made. So first of all, when I defined eta, I defined it in some way. I could have normalized it in a different way, right, by multiplying by some function of t. And also, when I chose the variable t, I said let's have a pole at 1 over t. I could have chosen some other parameterization, have the pole at some other function of t, right? And so, whatever you do, in both of these changes, lead to something that has the same kind of a differential equation looking like this, except that there are leftover terms here. So there's something that has an f prime of t times some function and a constant term. So the fact that this equation here takes on this specific form here characterizes both the normalization of the algebraic volume form and the specific linear choice of parameter in the pencil, 1 over linear, 1 over t. Okay. So what does this mean for mirror symmetry? Well, what this means is that, in the mirror context, we just have to, identify, the analogs of these structures here, and we get some differential equation, which will, of course, not be as simple as this. It will have remaining terms. And then the mirror map is exactly the transformation that brings the equation here into this form. Okay? In fact, that transformation singles out both the mirror map and the normalization of the Calabi-Yau structure. Okay, so what I'm actually talking about
So can I ask?
Yes.
So this W of t is a t-dependent function of
Yes.
x.
Yes.
So that equation is going to couple the coefficients of that function, right? Coupled together.
Yes,
So we're
yes,
taking
yes.
more complicated than just one function.
Oh, well, okay, I'm sorry. Okay. So when I say the Calabi-Yau vibration, I meant that the fibers are compact, and therefore, this is supposed to be proper. Okay? So therefore, all functions are actually functions with which are t-dependent. I mean, all the global functions are t-dependent. But you're right in that there are cases where there could be more than this. But I was just thinking of this simple case. Okay, so let's see what the mirror symmetry.
Can you say again, like this fact about what happened? Why all we have to do is whatever, and then we understand the mirror map?
Well, I'll show you what the mirror content is, and then I think it'll meet in the morning. So. I mean, basically, if you change the parameter, right? It's kind of a stupid thing. If you change the parameter from t to some psi of t, you substitute it in here, back in my calculus class, you will get an equation which looks roughly like this, but it has additional terms. Okay? And the only way you can get rid of the additional terms is to go back to the original parameter t. So there's some normal form which characterizes this particular parameter.
And why is it better than the usual Picard-Fuchs story?
Better, morally speaking. It's always, this equation always has the same form independent of what dimension you're in and so on. These are always the same kind of equations.
I see.
They're not some mysterious higher order differential equation. But I don't know whether that's better or not. I mean, that seems, I wouldn't say better. Okay, so
But your point is that the Form's equation doesn't care about anything about the variety thing, just somehow.
Well, I mean, it does. Let me show you the actual mirror. Okay. So let's look at the mirror story, and that'll be something that the symplectic geometry people can maybe. So take E to be an open symplectic manifold. Should be reasonably nice at infinity. And to make life simpler for me, and because anyway we're mirror symmetry, I'm going to assume that this is it. Okay? So there's a basic invariant symplectic cohomology. Which is a vector space, or a Z-graded vector space. Over some. Now I have it's traditional to be a little bit more specific, and I will call my formal variable Q. So it's A known Q. So they're serious, and you know the exponents go to infinity. I want to have, let's say I want to have both coefficients be real numbers. I'm not too picky about what I'm doing, but I do want it to have characteristic 0, and I want to be able to differentiate in dq direction. So this is a convenient case. So this guy here, I'm not going to explain how it is defined, but so this has the structure of the ring, and Lie algebra, gradient Lie algebra, and carries. Okay, but so it has a lot of structure, but the things that let's see. So it comes with a map. Say for topologies, it comes with a map from here, from the ordinary cohomology to this way. Okay? So-called acceleration. Okay? And so in particular, we have the identity here, 1, and it goes into something E, which is, in fact, the unit for the product structure. Okay? But there's also the cohomology class of the symplectic form, right? Which for convenience I will multiply with Q inverse. And this goes to a class K, which I will call, by analogy, the Hidara response class. Okay, so this is a basic symplectic invariant, and it is supposed to be the mirror of the Hochschild cohomology, and so all the other stuff that I said before also has mirrors. So there is an equivariant version. SH star S1 of E. So which is a you can forget the equivariance and land in the ordinary version. Again, this has this formal variable u of degree 2. Okay, so and there is that map. So this map here that you have, it actually lifts. So this is called, this one here is called acceleration. And this guy here, this map lifts here. Oops. Now comes this funny phenomenon in mirror symmetry talks where you erase something and then write down the same thing. So I'll write it down on a different board. So there's the Gauss-Manin connection. Gamma, from SH S1 of E. Oops, no, yeah, okay, yes. S1 plus 2, S1 of E, so it satisfies the same property here as that one, and it fits into. So this is sort of an operation of differentiation in dq direction. Okay, so so apparently it's supposed to do this thing here. There's the Kodaro-Spencer class, which is the cohomology class of the symplectic form. Okay. And now you say, whoa, mystery. But actually, you know, honestly, what happens in pseudo-holomorphic curve theory, right, is when you try differentiating it d by dq, what it basically means is that you take your moduli spaces where before you were counting points, and instead of counting points, you integrate the symplectic form, or you put an additional mark point and have it go through a divisor that's equal to this form. And therefore, this thing here is fairly natural, right? Was that? Plus 2. So the other thing which I probably should say, which I didn't have to say there, is we have the ordinary cohomology. Here, sorry for the space. And clearly, hopefully, we should be able to say what happens to ordinary cohomology classes. Okay. Yes, and so what happens, excuse me, I'm running out of space. This guy here, is that obviously if you have an ordinary class, you can just differentiate it by dq and multiply by u. Okay? And then there is, well, you know this guy here from standard mirror symmetry. There's the small quantum product with the cohomology class of the symplectic form. This is what's called the A-model connection. Okay? So we have this Gauss-Manin connection.
I think maybe you said, but you said it very quickly.
Excuse me?
I think you said, maybe you said it, but you said it very quickly, the definition of this Gauss-Manin connection.
Well, I didn't say it. In fact, as far as I know, this has probably never appeared before on a blackboard. Even though now that I said it exists, I'm sure all the experts are like, oh, yo, it takes some effort. Okay. So, but, well, one way to say this is to say that, you take Getzler's paper on the Gauss-Manin connection in non-commutative geometry, right? You take all the algebraic expressions that are there, and you write them as coming from some TQFT, and then that's what the TQFT does. Okay? But there are moduli spaces of things you have to count. Basically, in the simplest attempt, it would be like this. This is the cohomology of some chain complex. Okay, you just drew d by dq on that chain complex. And well, it's not a chain map, it's not compatible with the differential. But its failure to be compatible with the differential can be written as something that involves k. So you add some correction term, and then you keep going. So this in principle allows us to do the standard classical Gauss-Manin theory for these open symplectic manifolds. It's nothing exciting. Okay? So now I'm going to impose the assumption that k equals 0, which is different from the assumption there because I drew the box around. So then we'll have to talk, and I hope I don't run out of time too soon, about when you can actually expect this to hold, right? So this guy here comes from the cohomology class of the symplectic form. Of course, there are symplectic manifolds where the cohomology class of the symplectic form is 0, but it's not an interesting case for this thing. So the question is, well, are there ones where this is non-zero, but it goes to 0 in here? Okay, so if you have assumption, then you can actually define connections as before. I mean, everything is in fact, and so I can again look at this guy here. So you can do the same thing that I did there on the P model, which is to actually divide by U and get connections on the actual symplectic cohomology. Okay, and so this is what I'm interested in. Right. So so now let's look at a specific geometric situation, right? Otherwise, this is all blah blah blah. Okay, so and the specific geometric situation that I want to look at is the same thing as before, but now for symplectic geometers. Okay. So this guy here will be a symplectic Lefschetz vibration. Closed fibers. And let's assume, just for completeness, that the fiber of infinity is a smooth fiber. And now I'm going to say the same thing as before, which is that the first Chern class is percurritual to the class of the fiber. Okay? And so I'm going to define, so remove M. With C1 of E.
Fibers
Excuse me?
also.
The fiber also has C10. We're in the same, effectively, we're in the same situation as before, except now I'm going to apply symplectic geometry. So, I want to point out something. So there's a theorem. Of Chilibach and Jinyu and Chilibach and Urdu. Was that? From Felder and Albers, there you go. From Felder and Albers. Well, of course, they didn't actually prove this case here, but proof is exactly it's the same thing. Is that if you take this guy here, there you go, becomes an isomorphism after inverting.
The first collaboration has Chilibach also, I think.
Okay. Isomorphism after inverting. In fact, to be honest, this case is a lot simpler than the case that they did. Okay? So in the case that they looked at, it depends exactly on what you mean by S1 equivalent symplectic cohomology. But in this specific geometric situation, because this thing here is concentrated in bounded degrees, it doesn't actually matter which version you choose. And the proof is actually easy. So good. So what did I want to say? Okay. Also, what I already said is that it kind of enters into the proof of these guys here. So it's 0 in degree less than 0, and in degree 0 it's the same thing as. Okay, so any class in here, class X has a unique So okay, so now I want to say that maybe the only thing that's going to be interesting for symplectic geometers here. Okay, so there are actually other classes. So this thing here is a symplectic invariant of E, but from the compactification to E bar it requires certain additional structures. Okay, so there is compactification. A distinguished class here, S in SH naught of E is Ullmann Schrödinger class. Maybe this should be defined as an equivariant class, but it doesn't matter in this case because it's in degree zero. Okay? So essentially given by counting holomorphic curves going through the fiber that you just removed. Okay, so now I can ask you a puzzle question. Okay? So I have this class here, I lift it to an equivariant class. Okay? And throw away U torsion. So then it corresponds to some class in here. Some cohomology class. Which cohomology class? Similarly, since this is a ring, I can take the square and the cube and so on of this class. This gives me symplectic cohomology classes. I lift them to the equivariant thing, and they give me ordinary cohomology classes. Which cohomology classes? Well, so let's see. So the first answer to this to the first riddle is easy. So let's take S, so this class here, I lift it to the equivariant thing, and I multiply it with U, then I don't actually have to invert U, is equal to this guy here. What is this? So where Z1, so this is a class in the compactification, counts So there's a class, so in this case here, because of the fact about the first Chern class, if you look at the pseudo-holomorphic sections in any class, they span a codimension 2 cycle, and this is the class of that cycle, and you add up over all classes. Okay? Then you take this thing, you restrict it, and this is an ordinary cohomology class, but you consider it as a covariant cohomology class by a symplectic cohomology class by accelerating, and then that gives you this. So if I inverted U, I would just say S is equal U inverse this. Okay? But in fact, it's true without inverting. So as a consequence, I would like to point out to you that this thing here lies in the kernel of the ordinary map that just maps this thing here, right? If I take the because what happens here is the ordinary acceleration map is just if you take this guy, you throw away everything that's multiple of U, so you throw away this, there's nothing left. And this, in fact, was known. It's sort of at least somehow as a conjecture, it's in the literature. Okay, so this is here, and then the second guy here is unfortunately conjectural, and it's a mess, and I have no idea why. This is this guy here. So you take S, and you take the product, so it's a product in SH star of E. Okay, and I ask, what is this thing here? Where does it come from? So the answer is, well, you should multiply it by something, and then it's the previous thing that I stored. This is the quantum product here. Okay, quantum square plus U times Z 0, 1 E plus U squared Z 2 E. Okay, now I need color chalk. So this guy here counts bisections, and it's actually a cohomology class of degree 0, in other words, just a function of Q. Okay? And this guy here counts bisection tangent to the fiber of infinity. So it's a relative problem.
So what's a bisection?
A bisection is a rational map that has degree 2 over the base. Okay? And so these are general ones, and this is a cohomology class of degree 2 where you ask them to be tangent to 1, to the fiber of infinity. Okay? So this thing here, and this guy here, they're obviously the first two instances of a series of formulae, which I have no idea what they are, but I'm sure, Jinyu and Luis can knock your heads together, and you'll be there in no time. Okay? So, okay. So I am going to conclude this talk at some point. Okay? So, okay, so this answers part of these questions that I had to say that since we have this class here, it gives rise to certain cohomology classes in here, and which are, maybe not surprisingly, enumerative invariants, Gromov-Witten invariants of the bar. But it's still interesting to ask which Gromov-Witten invariants they are. Okay. So, there are functions of Q such that this is a degree 2 cohomology class, that's a degree 2 cohomology class. Okay, so this is something that takes place in the second cohomology application. Okay, so this is maybe the first. What is this guy? What's going on? Okay, so, well, the first thing to say is, why am I putting this guy in? Okay, so this implies that if I look at this guy here, right, this is psi times z1 restricted to E, right, just by restricting the formula to E. So it lies in the kernel of the acceleration. Right, because of the lemma. Because of that lemma. Okay. Of acceleration. Therefore, the Kodaira-Spencer class actually vanishes. Okay, so now I answered, when I introduced this assumption here, right there in the symplectic context, I said, well, we have to figure out when is this actually true. And so here there's some enumerative condition which ensures that this is always true. Now you have to say, when can this possibly hold? Right? But there's the really easy case, which is when this cohomology group is two-dimensional, right? Then it's, well, you have to, okay, so you have to assume something. Clearly, for this to hold, clearly this guy here has to be non-zero and this guy here has to be non-zero. Because this class cannot be equal to that class. This squares to 0. Okay. So there have to be a certain amount of holomorphic sections. Now this is not the talk I want to give, but there's an obvious source of these kinds of things, which is vibrations that you get by blowing up the base of a Lefschetz pencil. Because those have trivial sections. And if you look, those trivial sections, in fact, pretty much have this cohomology class. Well, the cohomology class of the trivial sections exactly would fit in here. So if there are no other sections, you're good. But, so anyway, there's a different story about when you can expect this to hold. It's not, you need a certain amount of holomorphic sections, but there's a large class of cases where this holds. And so in this case here, k is equals to 0. Okay, and there's things you can do when it does not hold, but this isn't the time. Okay, and now, what is going on here? Okay, so, conjecture. Again, actually, to be honest, it also assumes a bunch of other general stuff, which which I haven't worked out the details yet, but if it's general stuff, I feel much more comfortable, you know. If you can draw a commutative diagram, it automatically commutes. So, okay, so this, so if the assumption holds, the connection satisfies this. Take the unit, apply the connection twice, minus 2 times applying the connection 1 squared. Okay, this is the product in the symplectic homology, plus d cubed psi minus eta times this guy here, minus z. Okay, great fun. So psi and eta are the coefficients there. So they're essentially determined by this enumerative invariant z1. And there's the other thing, which is just a number, z2, the count of bisections. Where did this gentleman here go, which is a relative confidence invariant? Well, it's no secret that you can always express relative confidence invariance in terms of absolute ones. So as part of unwinding the formula, you unwind this thing here, and I don't have time to do it here, but in fact, that unwinding is where this combination here comes from. Okay? So I could have stated this guy here without using relative confidence invariance, but there would be some somewhat more suspicious looking term. Okay? So after all, if you're trying to prove this, it can't contain anything that you actually have no idea why it should be there. So you better look good. Okay, so let's see whether I have the other thing on the board anymore. I do not. Okay, so you remember the other equation here. F prime prime of t is 2f prime of t squared. Okay, so this is the same kind of equation, except it comes with random first order and zero order rubbish. Okay? But as part of the elementary theory of these equations, there's a unique transformation where you rescale E by some function of Q, and you change Q to some other variable T, which will get rid of these two terms. Okay? And that is exactly the mirror map. And so you can check that, you know, in simple examples, that actually gives you back the mirror maps for the Calabi-Yau hypersurface in a way that has, you know, nothing physically to do with, you know, standard force equation. Thank you very much.
Any comments or questions?
Is this conjecture supposed to be some sort of degeneration formula?
Yeah, I mean, I can tell you how this guy here is proved, right? So that the way that you start with is you start by looking at the non-equivariant theory. And there's, you know, you look at this guy here. This is a combination of two things. You count sections with a mark point. That leads to homology. And then there's this acceleration map, which is its own P. So you glue them together, and you see that there's a, you know, there's a null homotopy for that by moving mark points around. And then you think, well, but in the equivariant theory, you know, so this is derived from this null homotopy. You get this kind of term here as a secondary term. So you want to do the same thing here. You want to start by saying, well, clearly for the same reason that that is zero, this guy here is zero, right? But now when I add the correction terms and I multiply them together, I have additional things. So I wouldn't say that, I mean, it is possible to just say, okay, we reinterpret symplectic homology already in terms of probability theory, as in Dilber's thesis, and we do everything there. It wasn't clear to me that that was simpler than just, you know, I mean, I think this relation between symplectic homology and probability theory is actually more direct, because it manifests itself in terms of equalities of certain classes rather than isomorphism of spaces. So it is certainly should be, in principle, possible to just reduce it to Dilber's theory and SFT and so on. So in a sense, we already know it, I guess. But well, it's open, right?
Any other comments or questions? So if not, we'll thank Paolo again.